Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. In this video, we are going to delve even deeper into proving the limits of functions. And this video specifically is dedicated to proving limits of nonlinear functions. It is assumed that you have already watched the videos on the precise definition of a finite limit at a finite point, that you sort of understand that definition because it's going to be required as we move through here. Also, definitely, if you have not watched it, watch the Proving Limits for Linear Functions video. That will help understand pieces of what I'm going to be doing here. Proving limits for nonlinear functions is a little bit of a fun process. Actually, I really dig it, but often I find that students tend to be fairly intimidated by it at first, but once you get it, it's not too bad. It's kind of, like I said, fun. So let's dive into it. First of all, prove. Notice there's no new theorem or anything like that. Literally, we are just going to dive into a proof. Prove that that limit is true. First of all, check that that limit's true, because I have made mathematical mistakes in the past and said that something's true that's not. So let me just quickly write this down. Negative 4 being squared would be 16. Negative 4 times 8 is a negative 32. And then you add back 27. So we're at negative 16, add 27, that's positive 11. So, okay, this limit by direct substitution looks to be true. Now we're going to prove that this limit is true. And recall, just like I've done in the linear limits, proving linear limits, recall the definition of the finite limit at the finite point. That limit notation just means that any given epsilon that's been handed to us, which is positive, we can find a delta such that, which is also positive by the way, such that the distance between x and a being less than delta and greater than 0 will imply that the function's within an epsilon neighborhood of our limit L. All right, so let's go ahead and start our scratch work just like we had done in the linear limits video. So I will write my scratch work in red over here, scratch, and we are going to assume that we have arrived at this end statement. That's where we want to arrive, so I'm going to assume I'm there and I'm going to work my way backward to figure out what is the delta. If somebody walks in the room and says, hey, I know this is less than epsilon, then my job is to find the delta. All right, so we're going to assume here, and I need my pen, so assume that the distance between F and L is definitely less than epsilon. And what we want that the distance between X and A is less than some delta. That's our goal. We're working our way backwards. So again, we started here. We just want to work our way back to find out what this delta is. That's our process there. So let's go ahead and plug in the function and its limit, the function being x squared plus 8x plus 27. So I'll plug that in. X squared plus 8x plus whatever I said. And we're going to lose the limit 11. We'll assume that somehow we got that to be less than epsilon. Somehow. It was magic, right? Now let's do some simplification. So this implies, again, I'm just going to justify my handwriting here. I'm going to say simplify. Oops, except for you have to spell simplify correctly. I've only been spelling it that way for I don't know how many years. This is going to be the absolute value of x squared plus 8x, and then 27 minus 11 is a positive 16. And now you can see I need to get to an x minus whatever a is here. What is a? A is -4. So x minus a -4. X is approaching a -4, so we want the distance between x and -4 to be small. X minus a -4, or in other words, x plus 4. That's what we want to get. We get x plus 4 is less than delta. There we go. All right, that's our goal. Well, I know I can get an x plus 4 here by factoring. So this will imply, again, we're just factoring. We have the absolute value of x plus 4 quantity squared is less than epsilon. Now remember, I want to get just x plus 4, not x plus 4 quantity squared, but I could take the square root of both sides to get that x plus 4. So that's what I'm going to do here. Implies, again, I'm just going to take the square root of both sides, that I have the absolute value of x plus 4 is less than the square root of epsilon. I have arrived at what I want. I wanted to find out what is the distance between x and -4. I need that to be less than something. I found out what it is less than. It's less than the square root of epsilon. So that's going to be my choice for delta. Now at this point, you might be thinking, I thought you said this was going to be hard. It's not too terrible with this example, but it is a nonlinear limit, right? It's a quadratic limit. So let's go ahead and write out our proof. Again, when you write your proof, you're pretty much copying the definition almost verbatim. So I'm going to say for all epsilon greater than 0. The only part that changes really is as far as the handwriting here is I say let, because we are making our choice for delta. So let delta equal the square root of epsilon, because that's what we got in our scratch work. Remember, nobody sees that scratch work except for your professor and you. But otherwise, the world is just going to see your proof. And somebody comes up to you and they say, I want you to prove this limit is true. Just prove it to me. And you say, great. Well, give me any epsilon neighborhood. And they say, well, I'm not going to tell you that an epsilon neighborhood I'm going to give you. You just imagine it. I say, okay, well, whatever you give me, I'm going to choose a delta neighborhood of size square root of epsilon. And they say, why would you do that? And you say, because if x is really close to -4, and they say, how close? And you say, well, within my delta neighborhood. By the way, that's supposed to be equals there. Sorry about that. So within my delta neighborhood, well then, because I made my choice for delta to be the square root of your epsilon, well then, the absolute value of x plus 4 must be less than the square root of epsilon. They say, well, I believe you. Up to this point, I'm okay with that, since you were silly enough to let your delta equal the square root of the epsilon I handed you. Fine. Logically, that makes sense so far. And you say, great, thanks. But that will imply that the absolute value of x plus 4 squared is less than epsilon. And they say, okay, fine, whatever, I don't care. That's mathematically correct. I agree with you. They said, great, I'm glad you agree, because that implies the absolute value of x squared plus 8x plus 16 is less than epsilon. And they say, listen, this is not an algebra class. I don't care that you can square a binomial out. It doesn't really matter to me. You say, well, it should matter to you, because that's the same as the absolute value of x squared plus 8x. And off to the side, I'll cheat a little bit so I can look at my scratch work. Yeah, I want a plus 27 minus 11. So plus 27 minus 11 must therefore be less than epsilon. And they say, okay, what's your point? And you say, well, don't you notice? That's your function. And this is the limit. So therefore, you challenged me with an epsilon neighborhood about the function, about the point, whatever we were approaching. Was it 11? Yeah, you challenged me with the epsilon neighborhood about the height of 11. Here it is right here. So you gave me a really small epsilon neighborhood. I decided for my delta neighborhood about, oops, it was supposed to be about -4, so I'll just put it back here. I decided for my delta neighborhood about -4, I would choose a delta the size of the square root of the epsilon, whatever you handed me. And they say, you were okay with that? And they say, okay, well, fine. And you say, well, great. Just with that assumption that I built my delta neighborhood based upon your epsilon, I have forced the function to be within your epsilon neighborhood. And they say, wow, that's pretty amazing. How'd you do that? And you say, I don't tell my secrets. So QED, that is done. Quod erat demonstratum, so it has been proven. And notice we actually walked through the definition. We started with for all epsilon. We chose a delta. We then said, well, if that's true, then, and we went through a series of logical arguments to arrive at the distance between our function and our limit must therefore be less than epsilon. So it has been proven. That is a nonlinear proof or limit, a proof involving the limit of a nonlinear function. Now, I should say, if you are lost, if you were like, man, I still don't understand the precise definition of limit, he's done, 6 different examples and I still don't get it, then you should not continue with this video. You should come to my office hours or something like that, or email me, because the next example is going to be very hard for you. All right, so let's do the next example. That being said, here's another harmless looking, I say harmless, but it's not harmless, but here's a harmless looking quadratic. We're going to prove that this limit is true. Again, from the get-go, I'm just going to use the direct substitution property to make sure that it is actually true. And it is. Actually, I can easily see that's 6 minus 1 or 5, so that's okay. All right, so let's go ahead and prove that this is true. Remember that this is the definition we're working with. I'm going to continually write that, just kind of the more that you see it, the better it will work for you. And we'll do what we did last time. We'll just start with some scratch off to the right-hand side. We'll just go ahead and notice I'm going to write my scratch a little bit higher here because I'll need a little bit more room, I already know, for this. So let's go ahead and assume the distance between our function and our limit is less than epsilon. In other words, we have arrived at our destination right here. We just magically ended up there. We just want to know how, if somebody hands us the answer, we want to know how we got there. Basically, we got to the end. I want to know how we got there. We want to find the delta. Okay, so assume that that's true. And again, we want, whoops, except you can't really write very well with a highlighter. So let me try that with a red pen. We want the distance between x and a to be less than some delta that magically will show up, hopefully. Now, substituting in our function, this will imply we are assuming that the distance between 3x squared plus x plus 3 and the limit, which is 5, is less than epsilon. Now, if you're going to just skip this because you're like, oh, this is a repeat of the last one, you are going to be sorely, sorely disappointed when you reach the homework. You want to definitely watch this. Remember, our goal is to get the distance between x and -1 to be less than delta. So we want the absolute value of x plus 1 to be less than delta. let me repeat that. I want to get the absolute value of x plus 1 less than something. Let me repeat that. I want to get the absolute value of x plus 1 less than something. All right, here we go. This will imply via just simplification. I'm not going to write in, well, I'll write it in. Simplification. Simplify. The absolute value of 3x squared plus x minus 2 is less than epsilon. And you say, great, I'm going to use my factoring skills, which you should. Totally. So you go to factor and you get this. X plus, oops, let me use a parenthesis here. X plus 1 times 3x minus 2 in absolute values is less than epsilon. Great. Awesome. This is great. I get that absolute value of x plus 1, right? You could multiply this out and check my work. It is true. And by the way, you should also know that the absolute value of a times b is the same thing as the absolute value of a times the absolute value of b. So I'm going to break these into two absolute values. All right. And so now Notice that what I said, I highlighted and I repeated a few times. I want the absolute value of x plus 1 to be less than something. The biggest mistake people will make here is that they'll divide both sides by 3x minus 2 so that they can get x plus 1 in absolute value less than something. You cannot do the following. You cannot say, so not correct to do the following. It's not correct to say, oh, that means the absolute value of x plus 1 must be less than epsilon over absolute value of 3x minus 2. You do not know what x is. That could cause division by 0. Also, you need the absolute value of x plus 1 to be less than a constant, not a variable. And that's what makes this a lot more challenging than the previous problems, all of them in this entire section of material. So how do you rectify this situation? If you cannot divide by the absolute value of 3x minus 2, and if you cannot say the absolute value of x plus 1 is less than something with a variable, what do you do? Well, the answer is quite simple and elegant. You start by saying, you know what? I need to keep one of these, specifically the one you want to bound. So I'm going to go ahead the one that you want to keep, which is the x plus 1. So I'm going to say, keep this guy. That's what you want to keep. I'll bracket it up. I need to keep that because, well, I want the absolute value of x plus 1 to be less than something, as I keep repeating, right? And I am going to find out what's the worst case scenario that 3x minus 2 could be in absolute values. That is, I want to find a bound for this. Now, if I told you that you have a variable amount of money in your wallet, I guarantee I can create a bound on that. I could say it's less than $1 trillion. That's a pretty large bound, but I would be pretty much correct 100% of the time, right? I could even be pretty correct if I said it was less than $100,000. I could tighten up that bound if I wanted to. So if I could find out the worst case scenario for what that absolute value of 3x minus 2 is, then I can replace the absolute value of 3x minus 2 with that worst case scenario. Let me write that down. Our goal is to find a worst case scenario bound on the absolute value of 3x minus 2. What's the biggest it will possibly be? And there is a way to do this. You might say, but we don't know what x is, and you're absolutely correct, but we do know what x is near. So that will help out. We know that x is getting really close to -1. So it's not like x is going to be $1 trillion. That's not going to happen. X is getting really close to -1. So there is a nice, easy way to bound that absolute value of 3x minus 2. Then, if you find out what that number is, and let's call that number b. Let's say that the worst case scenario that 3x minus 2 in absolute value could be is b. Then you know the absolute value of x plus 1, which is right here, times the absolute value of 3x minus 2, which is right there. I'm just recreating this picture. You know that in the worst case scenario is less than, well, the absolute value of x plus 1, because, well, that's what we want to keep. And again, in the worst case scenario, the largest 3x minus 2 in absolute values will ever become is that b. That's a worst case scenario. But no matter what, this is still, in its worst case scenario, going to be less than epsilon. That is, the absolute value of x plus 1 times the worst possible case scenario for 3x minus 2 will still be less than epsilon. And guess what? These are both constants. So I can just divide both sides by b, and I would get this beautiful result. Now, I wish it were, and by the way, I'm not saying this is easy, but I am going to say I wish it were that easy. Don't give up yet, though. I'm with you this entire journey. So let's see what happens, how difficult it truly is. How do we make that bound? And what's the the dastardly situation that's going to creep up that I just hinted at when I said I wish it was that easy. So we'll go back up to this picture right here. I want to keep that absolute value of x plus 1, and I want to bound that absolute value of 3x minus 2. Now, there are a lot of approaches to doing this, but I really like my approach. So pay attention to how I do this. I'll write my approach, and I'll just keep it in red. Since x is approaching -1, it's probably a safe bet that x is between two very nice, pretty numbers. Always choose very nice, pretty numbers. If it's close to -1, then it's between -2 and 0. Now, that's an assumption, by the way. It's not necessarily true, but it likely is true. But it causes a little hitch in the giddy-up, a little like a ghost in the machine, if you will. And so I just need to make a caveat statement off to the side. Before I do, I want you to see that on a number line, if x is approaching -1 from the left or from the right there, then it's kind of safe to assume it's between -2 and 0. Notice that wiggle size there is 1. So I'm often asked, in fact, every single semester I've ever taught calculus, I've been asked the same question. Do you always pick a wiggle size of 1? And my response is you don't have to, but man, you'd be silly if you didn't. Like, why would you pick like a size of 1/2? You're going to have to do math with that. Just do a step size of 1 to either side. So whatever number the limit is approaching, just make an interval of size 1 on either side of it. You know that x will likely be within that interval. But here's the danger of doing this. We are making a massive assumption. So I'm going to point an arrow there, and I'm just going to say that we assumed right now that delta, and I'll call it sub 1, is equal to 1. In other words, we assumed we had a delta neighborhood, you can see it right here, of size 1. We've assumed that our x values are within a delta of 1, of x equals -1. And that could be a very bad assumption. And this is the ghost in the machine. This is the thing that kind of messes stuff up a little bit, but not a lot, actually. So again, I hope you're 100% with me. We're not anywhere near done, but I just want to keep you on the same kind of conversation as I'm at right now. So we start our proof by just restating the definition. And we go ahead and start our scratch work by assuming we've arrived at our destination there, that we have arrived at the antecedent is what we would call that. So I'm going to assume I've arrived at the antecedent. And I want to work my way backward to see what that delta is right there. Since I've arrived at the end, I want to see how I got there, basically. So let me scroll over. I'll say assume the distance between our function and our limit is less than epsilon. Assume we've arrived at the end. Then we started plugging things in. We did some factoring. And we noticed that when we did some factoring, we arrived at the absolute value of x plus 1. I'm just reiterating things, folks. And we needed that. We totally wanted that. But we needed that to be less than a constant. So dividing by the absolute value of 3x plus 2 is a no-no. Don't do that. And so here comes this kind of goal with anything nonlinear. We need to present ourselves with the worst case scenario on what 3x minus 2 in absolute values is going to become. And if we can do that, and we can find out how large that gets, if it gets to 100 or something like that in the worst case scenario, then we know that the absolute value of x plus 1 times that absolute value of 3x minus 2 in the worst case scenario will be the absolute value of x plus 1 times 100, if b was 100, which it won't be. That's a silly large number. So let's go ahead and do that. The way you do that is you say, well, I know what x is approaching. So that allows me to bound x itself. But when I bound x itself, I'm assuming that x is within a delta neighborhood of 1 from -1. So it's within a wiggle size of 1 from the x value of -1. Well, that's going to present a slight issue, but not much. But now I'm going to do something called rebuilding. I'm going to rebuild the absolute value. In fact, I'll say the absolute value of 3x, what was it, -2 or something like that? Yeah. I'm going to rebuild the absolute value of 3x -2. So I'll multiply all three sides by 3 to get 3x. So I'll get -6 is less than 3x is less than 0. Now I'm going to subtract 2 from all three sides. And that'll give me -8 is less than 3x minus 2 is less than -2. And now I'm going to say, okay, I got a number. Don't worry about the fact that it's 3x minus 2. In fact, I'm going to erase that just so that you don't concentrate on that. I'm going to call it happy face. You got some number. It's between -8 and -2. Tell me, just think to yourself or shout it out at the computer. How large is the absolute value of happy face? How large can it be? Well, if you take the absolute value of -2, that's 2. If you take the absolute value of -8, that's 8. The absolute value of happy face is between 2 and 8. Thus, I know in the worst case scenario, 3x minus 2 in absolute value is going to be less than 8. That's in the worst case scenario, as long as x is getting close to -1. And that's the caveat, as long as x is getting close to -1. So that is, we're within a delta of 1 of x equals -1. All right. Now I'm writing this out in language. This is not what I'm about to write. You would normally not write in your Scratch work, but I want this for your benefit. As long as x is between -2 and 0, well, 3x minus 2 in absolute values is bounded above by 8. We found a bound. Good for us. Pat ourselves on our back. Great, great, great. We found this large value of b. In the worst case scenario, that b is an 8, which means the absolute value of x plus 1 times that b must be less than epsilon, means the absolute value of x plus 1 must be less than epsilon over that b, which again is 8. So I'm just going to write that down. That implies the absolute value of x plus 1 times the absolute value of 3x minus 2 is definitely less than the absolute value of x plus 1 times 8. Again, because 3x minus 2 in absolute value at the worst case scenario is an 8. But no matter what, all of these statements are always assumed to be less than epsilon. We started with this whole process with the assumption that the distance between our function and our limit is less than epsilon. And the distance between our function and our limit ends up being this. We've assumed that that product is less than epsilon, no matter what. We have assumed that's the case. So even in the worst case scenario, we've assumed that the absolute value of x plus 1 times 8 is less than epsilon. Even in that worst case scenario. And so now we're going to go ahead and say that implies, whoops, although I'm not going to do that with a highlighter, and I'll do it with red ink, that will imply the absolute value of x plus 1 times 8 is less than epsilon. I should have written it over here, but I want it more succinct, so I'm just writing it there. Divide both sides by 8, and you have a bound, finally, for x plus 1 in absolute value. Remember, the goal here the entire time is to get the absolute value of x plus 1 to be less than something, and we just did that. So our choice for delta, sort of, is epsilon over 8. Now I say sort of because we have already called delta something else, and that's why I used delta sub 1, because I knew there was going to be a second one here. So really, I'm saying we're going to let delta sub 2 equal that. epsilon over 8. And you say, wait a second, hold on. Why do you have two deltas now? What is going on? Well, nothing actually. You have already done problems with two different epsilon or two different deltas. When we went to Desmos a while ago, somebody handed us an epsilon neighborhood and we started squeezing together a delta, and we found that if the graph was nonlinear, then we would get two different deltas. We'd get one side to work and the other side would not. And so we'd have two different choices of delta. A delta which is somewhat larger on the left-hand side in this case, and a delta which is somewhat smaller on the right-hand side in this case. And this is probably a better example even, because this was the actual one that I coded. So again, you're tightening this up and you get to a point where the left-hand side is good. That's your delta 1. And your right-hand side, just not good until you get to there. That's your delta 2. And you take the smaller of those two values. Smaller of delta 1 or delta 2. So you have seen this. And now is when we put it all together in a proof. Now you see all of my scratch work. Notice that I said every good mathematician, I said this a while ago, every good mathematician writes down all of their thoughts in their scratch work, because that's where they kind of figure out how to do things. And then when they do a proof, they make a very elegant proof that people look at and go, how the heck did they even know how to do that? So let's start with the elegant proof. Proof that the limit as x approaches -1 of 3x squared plus x plus 3 is equal to 5. Well, assume, notice I keep changing my language in my proofs just so that you have some practice with all the different styles. So assume epsilon, which is greater than 0, has been given. You don't have to write that. You can just say for all epsilon greater than 0. But I'm just showing you that not all proofs have to mimic every single instance of previous proofs, right? So assume epsilon, which is positive, has been given. Well, then we're going to choose delta to equal. Now remember, we had two choices of delta. A delta 1, let me go ahead and showcase that. Somewhere over here, right? Delta 1's right there, and delta 2's down below. So we had a delta 1 and a delta 2. You want to choose the smaller of those two deltas. So that's what I'm going to say. Choose the smaller of those two deltas. In mathematical language, that just means choose delta to equal the minimum of 1 or epsilon over 8. Now, just something you need to know before I continue this proof. If I give you two numbers, or and better yet, you give me two numbers. Any two numbers you want. So I'm going to write this off to the side. If you're given x and y, and if you say that some object, we said delta. Actually, I should just use delta here. If delta is equal to the smallest of those two, well then, delta is either less than or equal to x. Well, no, it's not either. It's less than or equal to x, and delta is less than or equal to y. Because it's the smaller of those two. Take any two numbers. If that was a 5 and a 7, well then, the smallest of those two is what delta is going to be. So delta is less than or equal to 5, and it's also less than or equal to 7. Totally makes sense. So just letting you know that whatever this returns, this minimum function returns, it forces delta to be the smaller of those two numbers. And so that really works out. No matter what delta is, it will always be smaller than 1 and smaller than epsilon over 8. And when I say smaller, I actually mean less than or equal to, but we're never going to use the equal to sign other than this moment in this proof. Now we have to do something with that statement. Well, you happen to know two things are true. First of all, and actually before you even get to the things that are true, if you just check off what you did here, we already said for any given epsilon, we've already stated what our choice of delta is going to be. So let's go ahead and just make this blanket statement here. So we'll go ahead and say, if 0 is less than the absolute value of x plus 1, because that's x minus a negative 1, right? If that's less than delta, then two things are true. Remember, delta is the minimum of 1 and epsilon over 8. That means that the absolute value of x plus 1 is less than 1, and the absolute value of x plus 1 is less than epsilon over 8. Again, because because delta is the smaller of those two values. So by this aside, delta will be less than or equal to x and y. And since the absolute value is less than delta, well, then the absolute value is going to be strictly less than x and strictly less than y. And there you go. Just think about that. It's hard enough to say it, but yeah. I highly recommend always starting with this guy. It just works much better. So I'll showcase what I mean. So if it's the case that the distance between x and negative 1 is less than delta, then it must be true that the absolute value of x plus 1 is less than 1, because delta is equal to the minimum of 1 and epsilon over 8. But if that's true, then, so taking this guy, I'm going to write this implies that x, well, this is telling me that x is really close to negative 1, right? This is x minus a negative 1. So we're really close to negative 1. How close? Within 1 unit. So that means that x must be between negative 2 and 0, because it's a delta neighborhood of 1 around x equals negative 1. And notice what I'm about to do. Look at my scratch work over here. I'm about to copy some red ink. I'm about to build me a 3x minus 2 in absolute values. So at this point, I start copying my scratch work. I say, you know what? In fact, I'm gonna say it like I would say it in a courtroom. Ladies and gentlemen of the courtroom, I know I've been challenged. I've been tasked with proving to you that this quadratic expression will become or get very close to 5 as x gets close to negative 1. And they say, yes, you have been proved that you've been challenged with that, even though the jury can't talk. And you say, well, I tell you what, somebody has come in and handed me an epsilon. Are you okay with me assuming that any epsilon neighborhood, any size epsilon neighborhood has been given? And they say, yes, we can't have you assume that an example epsilon has been given. It has to be general. It has to be any epsilon. And I say, okay, fine. Well, no matter what, ladies and gentlemen, I'm going to choose delta equal the minimum of 1 and that epsilon that I don't know what it is, but epsilon over 8. So the minimum of 1 and epsilon over 8. And they say, why? Why? And I say, because if x is really close to negative 1, and they say, how close? And I say, well, within a delta neighborhood of negative 1. Then I hope you, ladies and gentlemen of the jury, would agree with me that if x plus 1 is less than delta, then it has to be less than 1. And it has to be less than epsilon over 8. And they say, okay, after some thought, because they're not in calculus, so they may be a little bit lost on it, but it takes them some time, and they finally figured out, okay, yeah, I agree with you that both those conditions have to be true. And you say, great. But ladies and gentlemen of the jury, you told me that you believe that the distance between x and negative 1 is less than 1. They nod their heads, yes, of course. So you're saying that if I built a neighborhood around negative 1, I can include all values within a distance of 1 away from it. And they nod their heads. And you say, well, that's why I have this inequality. And they say, okay, well, how special or important is that? And meanwhile, you're looking at your notes on the side while you make this argument. And you see that little inequality, triple-sided inequality right there. And you say, well, ladies and gentlemen, I'm going to show you some fantasticness. And they say, that's not a word. And you say, I don't care. And you say, because I'm going to take this and I'm going to multiply all 3 sides of this triple-sided inequality by 3. And they nod their heads and they say, I remember algebra, of course. And you say, great. Well, if you remember that, then you remember how to subtract. So I'm going to subtract 2 from all 3 sides. And they nod their heads and they say, great, fine, who cares? This is not that big of a deal. Super easy. Well, I don't know if they would say that. And meanwhile, again, all you're doing is copying your scratch work. And you say, ladies and gentlemen of the jury, If I told you that your bank account had a deficit of somewhere between $2 and $8, what's the maximum number of dollars that you have in debt? And somebody smart says, well, 8, because you were between -2 and 8. -8, that is. And I say, yes, you're absolutely right. So the maximum debt you have, the maximum absolute value of this is 8. You're absolutely right. The maximum size of that unknown piece in the center is 8. And they say, okay, get to the point. And you say, well, I'd love to get to the point. But I have to remind you, ladies and gentlemen of the jury, that you told me you were okay with the distance between x and -1 being less than 1. And you were also okay with the distance between x and -1 being less than epsilon over 8. And they all nod their heads and you say, well, just to remind you, it's because you said delta was equal to, or because I told you that I'm choosing delta to equal the minimum of 1 and epsilon over 8. And they say, yes, of course. Get to the point, just like you're probably doing. And I say, well, if I multiply both sides of this inequality by 8, would you be okay? And they say, yes. And you say, great. Ladies and gentlemen of the jury, would you please inspect that inequality and tell me if I've done any hocus pocus? And they say, no, you have not done any hocus pocus. And you say, but ladies and gentlemen of the jury, were you just witness to me saying and you approving that whenever you see the number 8, it is always greater than the absolute value of 3x minus 2? And they look astonished for a brief moment. And they say, yeah. You say, okay, well then, I hope you don't mind me saying, and I'm going to take the liberty of doing it here, that you just told me that all other things being equal, the x plus 1s and absolute values being equal, that this statement must be greater than the absolute value of 3x minus 2 times the absolute value of x plus 1. Because again, you've told me you're okay with 8 being greater than 3x minus 2 in absolute value. And they say, yeah. And you say, okay, great. Well, that implies, ladies and gentlemen of the jury, if you don't mind me multiplying out this binomial, it implies that 3x squared, minus 2x plus 3x plus x minus 2 in absolute values, because that's what this is right here, is therefore less than that epsilon. And they say, yeah. And you say, but ladies and gentlemen of the jury, and you look at your handwritten notes, just to make sure you're matching up with your scratch work, you say, well, ladies and gentlemen of the jury, that means that logically, step by step, you've agreed with me 100% of the time, and you're willing to also agree with me, likely, if you know arithmetic, that this can be written in this form, right? 3x squared plus x plus 3 minus 5. And they say, yeah. And you say, well, ladies and gentlemen, you gave me an epsilon neighborhood where I was supposed to put my function or bound my function into that epsilon neighborhood, specifically the distance between my function and the limit. That's what you challenged me with, right, ladies and gentlemen of the jury? And they say, yes. And you say, I have just done that. This is f, and this is the limit. All I assumed was that delta was either the minimum of 1 or epsilon over 8. No matter what, in either case, I will bound my function to within the epsilon neighborhood that you choose of the limit. Quite easily done. Quod erat demonstratum. I love that jury talk because it's just kind of fun. But it is pretty amazing. If you just look at the proof, that is a slick proof. And when somebody looks at that, most calculus students will look at that and just kind of, at first, probably cry. Honestly, I remember I had a tough time with epsilon delta proofs. But it really is super powerful. All right. Now, that's the only example I'm going to do. Have a good day. Just kidding. I will do yet another example because I don't think one is enough. And here's the problem, by the way, with doing anything via video where you're not you don't have a live audience, it's very difficult to get the feedback. So as I was going through that, I was trying to answer the questions that I know get asked quite often. And so again, I will do that here. Prove the following limit. So you, being diligent, you write down the definition of a limit, the finite limit at the finite point. For all epsilon greater than 0, there must exist a delta that is positive, such that as long as the distance between x and a is less than delta, that should imply the distance between your function and your limit is less than epsilon. If you could just do the proof and run through it, that'd be awesome, but you won't be able to, because this is a cubic, which is slightly more complex than the last one. So we're going to go ahead and do our scratch work. It has the same feel though. The scratch work will feel very, very similar to what we just did. All right, let's go ahead and assume that the distance between our function and our limit is less than epsilon, and we want to eventually find out how we got there. Specifically, we want to find out how we got a delta so that the distance between x and -2 is less than that delta. So let's go ahead and do this. Again, remember, I want to arrive at the absolute value of x plus 2 being less than some finite, again, constant finite number. Very important. All right, so let's see the distance between the function and the limit. Let's go ahead and write that down. The function, well, that's not bad. That's x cubed minus 1 minus the limit, which is a -9. We're assuming that's less than epsilon. This actually doesn't look too terrible. That implies, I'm not going to write out all the language here. I'm just going to say that implies that x cubed plus 8 is less than epsilon. Oh, well that I can factor. That's a sum of cubes formula. It's super nice. Required formula to remember from algebra 2 or algebra 1. X squared minus 2x plus 4. And absolute values is less than epsilon. Great. Again, working my way backward through the definition. I assumed this piece right here. I want to somehow figure out what is the bound on x minus a. What is that constant? I'll split this product apart into the product of two absolute values. And again, I will arrive at a really sticky situation. I want to keep that, and I want to bound this. I want to find a number. What's the worst case scenario for that, right? So I want to build a bound. Now, the last problem I spent forever kind of really building up the theory and the concepts here, but now, no need to. I can now that I have your faith and your trust, hopefully, I can now do this. All right, so let's try. I want to find the worst case scenario for that blue highlighted region. Well, since normally in your Scratch, you don't write all this language here that I'm about to write down, but I still think it's beneficial for you. So since x is approaching -2, right? Yep. Since x is getting really close to -2, we can assume, remember what assuming does, so there is a problem with it, but we can assume that x is between, just think of a wiggle of size 1 centered at -2. It's between -3 and -1. Now off to the side here, I make a note to myself because I use that word assume. That means I've made an assumption about delta. I've made the assumption that delta is probably a size of 1. I've created a delta neighborhood of size 1 with that assumption. But now I'm going to go ahead and now that I have a bound on delta, I'll start rebuilding this trinomial. Now, generally when you're rebuilding a trinomial, or actually rebuilding any type of absolute value like this, you deal with the linear factors first, or the linear terms first, and then the quadratic terms in a totally different inequality. So I'll showcase that here. So since I know that x is between -3 and -1, if I want to rebuild, and I am going to write that word just so that you know what I'm doing. If I want to rebuild that trinomial, I'll start by multiplying all three sides by a -2. I have the x, so let me just multiply it by -2. Some people will ask, why didn't you square it? I will actually, but I'll do that separately if you don't mind. Actually, you know what? I'll do that now since you asked, and you didn't even ask. But I'll do that. I'll just read this from left to right, just so that I don't screw you up. So this will imply that x squared is between two numbers. Well, if you square this, you'll get 9. You square that, you'll get 1. So I guess x squared is between 1 and 9. Notice my inequality signs. Super duper important. If you don't switch those inequality signs, you don't know nothing about numbers, right? Because there's no way that 1 is greater than 9. So you got to know to switch the inequality signs, okay? So there you go. For the people in the crowd that wanted me to start here, I did it just for you. This one is for you. All right, so now I continue forward. I want to subtract 2x, but the problem here is I can't. If I subtract 2x from all three sides right now, I'll have a 9 minus 2x, x squared minus 2x, and a 1 minus 2x. I don't want to bound that by variables. So because of that, I'm going to build a secondary inequality. I'll just grab this guy and say, guess what? That also implies I'm going to multiply all three sides of that by a -2. If I do that, -2 times -3 is 6. Remember, you multiply it by a negative, it'll flip the inequality, -2x, and again, flip the inequality, -1 times -2 is 2. So now I've taken care of not only the x squared, but the -2x. And now to that -2x, I'll just add 4 to all three sides. And this will imply, if I add 4 to all three sides, I get this. -2x plus 4 is greater than, add 4, 6. And you say, man, that's a lot of triple-sided inequalities. I say, yes, but let's glue things together so we can get back to bounding that trinomial. I just need to grab this x squared and this -2x plus 4 and add them up. Super important thing to remember here, and I think it's well worth just writing this down. When you add these up, you got to make sure that their inequalities are pointing the same direction. And I'll give you an example here off to the side, but I'm just going to write it like this for now. When you add these up, make sure again that these inequalities right here and here are pointing in the same direction. They're all greater than in this case. Very, very, very important. Adding that up means that the largest this summation will be is 19. The summation itself is x squared minus 2x plus 4. And that is greater than 1 plus 6 or 7. Now, I'm going to finish this out and then I'm going to come back and talk to you about why those inequalities have to be matched up. So in absolute value, what's the worst possible case in absolute value that the x squared minus 2x plus 4 will ever be? What's the largest positive number that will ever be? Well, if you look at this ranges from 7 to 19. It should be fairly obvious to you that the largest worst case scenario is that that's going to be a 19. And guess what? We have found our bound. We've bounded this by 19. We know that in the worst case scenario, as long as we're in our delta neighborhood, worst case scenario is that's going to be a 19. So what I'm going to do is say that means that the absolute value of x plus 2 times the absolute value of x squared minus 2x plus 4 is less than the absolute value of x plus 2 times 19. Because again, in the worst case scenario, it grows to 19. That's the worst case though. It's usually less than that. But no matter what, we have assumed that this will be less than epsilon. That is, we have this absolute value of x plus 2 times 19 must therefore be less than epsilon. Divide both sides by 19, and you have found delta 2, a second delta. The first delta was just an assumption because we're assuming x is really close to -2, which it likely is, honestly. But the second one covers all other cases. Okay, fine. If x is not within that delta neighborhood of 1, fine. Then I'll just let my delta be epsilon over 19. I will defeat your epsilon every time. So let's see how this works. Actually, before I do, I want to justify something here with those inequalities. So I did say that you want those inequalities to face the same direction. So I hope you all agree that 3 is greater than 1. I hope you also all agree that, I don't know. Now I have to think. There we go. I just multiplied all three sides by -5. I hope you all agree that when you multiply all three sides by -5, you get -5 is greater than, because you multiply by a negative, -5x, which is greater than, because you multiply by a negative, -15. Now, it would make no sense to add these up as they're written. You have to realign them. So if you're going to add them up, actually, let me do it in a different ink so it stands out for you. If you're going to add them up, make sure that you have their inequalities going the same direction. See what I did there? 3 is greater than x is greater than 1. But now that everything is lined up and the inequality signs match, I can now say, oh, -5 plus 3 is a -2 is greater than -5x plus 1x is a -4x, which is greater than -15 plus 1, which is a -14. What are you going to do with that? I don't know. I don't know what that number, why. That has nothing to do with this problem. This is an aside. So I'll just say aside. But just an aside so that you know, align your inequalities before you add things up. That will be a headache. You will find that you'll get wrong answers and you don't know why, and then you'll look back and go, oh, I didn't get the inequalities working right. So make sure you have that working right. All right. I did a lot of talking. Still, I could barrel through this in a minute, but I'm not, because I'm trying to drag you through the sand on this, right? So now let's go ahead and actually do the proof, because we have our deltas. So, ladies and gentlemen of the jury, see what I'm doing here? I'm going to pretend as though you're a jury again. I just don't know why. I guess in an alternate life, I was probably a terrible lawyer. I wish I wasn't, but I probably was, right? So, ladies and gentlemen of the jury, I hear tell that you want a proof that the limit as x approaches -2 of x cubed minus 1 must equal -9. And I must admit to you that today I'm here to do that. So I ask you, ladies and gentlemen of the jury, to please give me any number greater than 0, any epsilon you want. And the jury remains silent because the judges told them, don't give him an epsilon. Let him work for his fee or whatever. Well, very well, ladies and gentlemen. Then I will assume that you've handed me an epsilon. I don't know what it is, but I'm going to perform some hocus pocus. And the entire time, I will ask you if you believe me. So for any epsilon that you hand me, I will choose my delta to equal. And by the way, at this point, some people are like, what is delta? What is he talking about? Don't worry about that. I will choose delta to equal the minimum of 1 and epsilon, the one you didn't hand me, but the one you will hand me, over 19. And they all kind of sit there, not in stunned amazement, but just kind of like, okay, whatever. Remember, I chose my delta 1s, by the way, and my delta 2 from our scratch work. That's right here and here. Now I go back to the jury. Well, ladies and gentlemen, I hope you'll forgive my notation. It's logic, symbolic logic notation. I highly recommend you take a course in symbolic logic because it's an amazing course. However, if it is actually the case that the distance between x and whatever our x is approaching here, which you told me you want x to approach -2. So if it is the case that the distance between x and -2 is less than delta, the delta that I have presented to you, then, well, surely you have to admit that that absolute value of x plus 2 must therefore be less than 1 and simultaneously less than epsilon over 19. Somebody in the jury box stands up and they say, no, because it could actually equal 1 or it could actually equal epsilon over 19. And I say, yeah, that is true. Delta could actually equal 1 or epsilon over 19, the smaller of those two. However, the absolute value, good sir, who's just yelled at me in the middle of a courtroom like a jerk, the absolute value is strictly less than delta. So if you'll forgive me, but I have to disagree, the absolute value is going to be strictly less than 1 and simultaneously strictly less than epsilon over 19. And they say, oh, forgive me, I'm so sorry. And I say, that's okay, it's cool. All right, cool your jets. Okay, and then I go back to the proof and I say, well, since everybody agrees with me that these two statements are true, this first statement, which I will number 1, why not? And I'll number this 2. Not that I have to, ladies and gentlemen of the jury. I could do this entire proof without that magical number 1 or 2, but because I think it draws your attention to what I'm working on a little bit better. So if I'm talking about number 1 here, number 1, wouldn't you agree, since x is approaching -2 and we're saying the distance between x and -2 is less than 1, wouldn't you agree, ladies and gentlemen of the jury, that x must be between, therefore, -3 and -1? Again, we're allowing x to approach -2, and in this first case, that distance is less than 1, so x must be between -3 and -1. And they kind of nod their head, okay. You say, well, I tell you what, and you look at your notes as you start doing the rest of this. You don't show them though. You're one of those lawyers who goes to the podium every once in a while, glances down. So you glance down and you see, okay, here's where I am right here. So I know I'm going to have to square, and I'm also going to have to multiply by -2 and add 4. Okay, got it. Well, ladies and gentlemen of the jury, if you know that x is between -3 and -1, you all agree with me, especially that nice guy in the back who yelled at me. So you should also agree that x squared is less than 9, but greater than 1. They stare at that for a moment and they kind of nod their heads. Okay, I agree with that. Yeah, okay. But I'm also going to tell you, ladies and gentlemen, that had I just taken that same inequality and just multiplied everything by -2, I would have gotten this. And they say, yes, of course. But somebody stands up, little old woman, and she says, what about that x squared? And I say, well, don't worry about the x squared. I'll get back to that later. But let's focus on that -2x for a moment. I'm going to add 4 to all 3 sides. I hope you don't mind. She says, no, I'm good with that. All right, great, thank you. And so I add 4 to all 3 sides. Ladies and gentlemen of the jury, I really like the interactiveness that you're showing. I don't even know if that's a word, but I'll present it as if it were, because I'm a lawyer and you'll be convinced if I say so. And you have all nodded your head and said you agree that these two inequalities must hold as long as x is between -3 and -1, which you told me is true because you told me the distance between x and -2 is less than 1. So if those two inequalities are true, their sum also has to be true. Now, some people might be lost on this, but you can convince them that if two inequalities are true, their sum has to be true, and they all kind of nod. So you say, okay, well, I'll add those up. That would imply 9 plus 10, which is 19, is greater than x squared minus 2x plus 4, which is greater than 6 plus 1, which is 7. And the old lady in the back says, ah, there it goes. Thank you. And I say, okay, sure. Not a problem. And then I say, but little old lady in the back, wouldn't you agree then that the x squared minus 2x plus 4, its maximal value, its maximum magnitude, actually is what we'd call it, is 19. In other words, it will grow all the way up to, but not including 19. And she nods her head. Of course, any fool knows that. I say, well, I am such a fool. And so I then stop there and I pause for effect. I like to pause for effect every now and again. So here I'm going to pause for effect. And then I say, ladies and gentlemen, I forgot to tell you, it's been a while since we visited this statement right over here. Why don't we go ahead and go to that statement? I'm so interested in what you think about it. Do you mind if I multiply both sides of this statement by 19? And they say, no, that's okay, I guess. I say, great, thank you. But why would you do that? Well, I'm not going to tell you until I get there. You'll just have to hold on to your seat. Wait. Do you see something similar between where we paused and where we're at right now? And a young lady in the front row says, they both have 19. I say, of course, student in my calculus class who I paid to be here. Yes, they both have a 19. And that's very important because we have already shown via logic that 19 must be greater than this picture. Everybody nods, of course, yeah. So I hope you don't mind that I say this 19 must be greater than that picture. And they say, how are you going to do that? And I say, well, I'm going to leave some space because it's just easier to write it with some space here. So I'm going to say, here's my 19 times the absolute value of x plus 2. It's less than epsilon. But that 19, all other things being equal, I didn't even leave enough space. All other things being equal, so the absolute values of x plus 2 just still hang out. That 19 is greater than that highlighted absolute value of x squared minus 2x plus 4. And everybody stares. They say, ooh. And then some guy in the back says, I don't get it. I said, don't worry. I'm going to help you out, sir. You will get this very soon. So I hope you all agree that the absolute value of x squared minus 2x plus 4, since we've driven you to this point, times the absolute value of x plus 2 is therefore less than epsilon. Here's the epsilon. Here's the greater than sign. Here's the stuff I just wrote down. And they all nod their heads. And I say, well, now I'm going to take you back to algebra. Kick it old school. We're going to multiply this out. Here we go. Multiply, multiply, multiply. That's x cubed plus 8. Omni, omni, omni. And they stare at that and they say, wow, that compresses super nice. And I say, yeah, it sure does. You know what's also nice about that? Let me look at my scratch and I'll tell you. That is the absolute value of x cubed minus 1 minus a negative 9. It's less than epsilon. And some old man in the back says, I don't get it. Why'd you write that? All of this jury is from Arkansas, by the way. And I say, well, because you see, I can say that, by the way, my grandfather's from Arkansas. So I say, you could see that x cubed minus 1 should be somewhat familiar to you, sir. In fact, that x cubed minus 1 is right here. And that negative 9 should also be familiar, because there it is right there. The x cubed minus 1 is my function, and the negative 9 is my limit. So let me go ahead and just say, all our logical arguments imply that the distance between the function and the limit is less than epsilon. Or in other words, my function is within the epsilon neighborhood that you refuse to give me. I have magically done it without you even handing me an epsilon. Now, no matter what epsilon you hand me, I will defeat you. Q, E, D. That's me dropping the pen because I don't have a mic to drop. It's actually bolted to this desk here on a little arm, and it kind of swings out. And if I were to drop it, I'd be very sad. And of course the crowd, they rejoice because they all know calculus, because every jury does, you know how that works. And they're super happy. And we have proven it. There's a roadmap. Every step of the way has been mapped out for you. So I've given you two of the harder examples. Now I'm going to give you a theoretical example. This is an awesome problem. We're going to let the function, yes, I know it's an hour and 11 minutes or how many minutes into this, but this is the deepest part of Calc 1. You are in deep waters right now, and I want you to have as much ammunition to swim through the sea of sharks. None of that analogy worked, by the way. Just telling you that. So we're going to let f of x equal this piecewise defined function. The function returns a 0 if you plug in a rational number like 1/2, 0, 15, -34/7, stuff like that. Otherwise, it's going to return x squared if x is irrational. Square root of 2 is irrational, pi, e, those types of things. So, does the limit as x approaches 0 exist? If so, what is its value? If not, why doesn't it exist? Make sure to justify your answer carefully. Now, that word justify is kind of what's the word I'm looking for? That word justify is a little bit of a sticky word, because justify is not as strong as proof. So if I said prove your answer, then you probably want to go to the limit definition that we've just gone through. However, it's not actually necessary here. So you might think, well, why do you even have it in this section? Because I want you to think. Stop asking that question. All right. So what do you think the limit is as x approaches 0 of f of x? Well, this is what the graph looks like if you were to graph it out. It looks like, remember, whenever you plug in a rational number, the output will be 0. So plug in 0, it'll get out a 0. Plug in 1, it gets out a 0. Plug in -1, 2, -2, 1/2, 1/4, right? Everywhere on this number line where you plug in a rational number, a fraction, number that can be represented as a fraction, the function just lands on the x-axis. However, just to let you know, there are infinitely many irrational numbers. And in fact, between that's the wrong order of that statement, but between any two rational numbers, pay attention to this. This is really a cool idea. Between any two rational numbers, like 1/2 and 1/3, wrong order on that. I'll just do it over here. Between those two rational numbers, there's an infinite number of irrational numbers. Between any two rational numbers, there's an infinite number of irrational numbers. So what I'm trying to tell you is, between any two dots right there, there's an infinite number of irrational numbers. And if you start plotting out what they go to x squared. So you have something that looks like this, where I'm plotting are the squares of irrational numbers. So you get this function that you have to constantly plot points to graph. But if I were to zoom out, it would look like a parabola, to be very honest with you, because it's got an infinite number of holes in it, but you can't see them because they're only at points. It's kind of an interesting function. However, as x gets really close to 0, what are the y values approaching in any case? And if you say 0, I would say, good for you. You're absolutely correct. As we get close to 0, as far as inputs, the outputs approach 0. So you could do this using an epsilon delta proof, the proofs that I've been doing. However, I want to showcase that you do not have to always rely on the epsilon delta proof. So why or how or what can you do, right? Well, here's the deal. F of x is always greater than or equal to 0, isn't it? I mean, look at the drawing. It's definitely always greater than or equal to 0. Okay. And it's always less than or equal to what? Well, you can't say 1 because that's not true. Because if you plugged in the square root of 7, that'd be 7 when you square it. So that's not true. However, if you just said it's less than or equal to x squared, you would be true. You would be true. You would be correct. Man, it's been a long day. So, notice I've created a triple-sided inequality, and now I'm going to pull something out from the past. The limit as x approaches 0 of 0 is equal to 0. Yeah, that's right. And the limit as x approaches 0 of x squared, that's 0 as well. Of course. Thus, the limit as x approaches 0 of f of x must be 0 by the squeeze theorem. Ha-ha! I know, you think I'm very excited about math, right? I'm giddy because I've been doing videos all day and I'm just beat down. All right. So this showcases that you do not always have to prove a statement using the epsilon delta proof. The times you do have to use the epsilon delta proof is if you're specifically asked to prove a limit is true. So it is incredibly important that you know, like if I say prove this limit is true, then you have to use an epsilon delta proof. So I think this is really more than enough. I had another page, but you know what? I'm not going to bother. I'm going to go ahead and just stop here because I think that's just enough for my voice, brain, and for your brain as well. So I really hope you've enjoyed the fantastic world of epsilon delta proofs brought to you by Professor Simpson of Cosumnes River College in Sacramento, California. And our next lecture video, which will almost finish out this. Actually, we're going to do two things in the next lecture video. We're going to do proving single-sided limits and then the precise definition of an infinite limit at a finite point, which is somewhat fast.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and